machine learning type of workflows. And Anastasia will tell you all about that. I just wanted to start off with something first. That would be pretty much the last tooling part of this workshop. So what Julia offers us to have sustainable workflows. And this would be mainly about how to record our setup to make sure that it's reproducible, and how to do the same with our data. So be able to save and load data without losing. Let me open my REPL again. We will use the same that we talked about yesterday. So we just add that to my environment. And I will load the dataset the same way as I did yesterday. Oops. Just to work with only numerical or string data, I will drop the missing parts again. And as we were saying yesterday, we have these numerical fields that are the big build length and the build depth, as well as body mass and flipper length and so on. So now let's imagine that we did some computation, we did some data pipeline to do some, processing to our data. We're interesting to have, in order to have a reproducible setup, to save two things. One is the environment, so the software, all the packages that we used, and a snapshot of the libraries that we imported, and so on, and the data itself, of course. So to save the environment, let's add the package API. We can look at package.status. And this will tell me which packages are present right now in my environment. So you can see that I loaded a few in my default environment. I didn't activate anything else. So now I'm sitting in my, what you would call the base environment, for example, if it was Conda. And these are all the packages that I added to it in this Julia installation, pretty much. And the state of the environment is recorded by two files in Julia. There are the project.toml and the manifest.toml. If you're not familiar, TOML is a simple markup language. It's kind of similar to YAML, and belongs to the family, so to say. And why two files? Well, one, the project.toml is the one that ideally you would like to share with someone if they were to try to recreate your setup. And this is also the one that actually was present in our introductory onboarding lesson. So this is the way that we shared which packages would be needed during this work. The manifest.toml is kind of similar, but it records the exact versions of the packages and plus their dependencies. So if you want to exactly recreate an environment, both of them are needed. And every time we add a package using the REPL or using the package API, Julia saves automatically or updates automatically these files. And if you want to replicate environment, this is what we like to share. So I can show you, for example, how the ones for my base Julia environment that I'm using now look like. And this will be sitting in Julia environments. I'm using 1.11. So I have, well, some local preferences, manifest and project. So they will look the following. This is my project.toml. I don't need to bother, creating this from scratch. These individual hashes that represent the packages are added automatically by Julia every time I write something like package.add. And of course, these packages come with their own dependencies and that are called in a specific version. So to look at that, I can open the manifest.toml file. And you can see that this is a lot more involved because it calls the dependencies that are needed by each package that can come with their own artifacts. This is really, really advisable to not modify by hand since it's created by Julia. But yeah, this is what you will share if you were to recreate your environment. And so far, so good. So if you want to recreate a package, you copy these two, an environment, you copy these two files to the new location, maybe another computer or just another project that you're working on. And once the files are in that folder, you can do package.activate. That is more or less what we did in our introductory onboarding lesson. And then instantiate will, download all of them and deploy them. And this works and it's useful in itself. If you're having something that has to do with, for example, more scientific academic workflow, I would suggest to use this package called Dr. Watson. And I will paste the link to it in a few minutes. This has some nice infrastructure because once we initialize the project, there is a nice tutorial about all of this works. We'll create a nice folder tree structure for us where the data is saved in certain locations. We can have plots, notebooks, the scripts that we write, some testing. And by default, you also can upload to GitHub. So every change that you make to your code will be recorded. And this, I would say, guarantees a lot more true reproducibility of science. Because if with this, every change to the code is recorded. So at any given time, you have the code and the associated data, or the data and the associated code, actually. So this allows for true reproducibility. So I would say if you were to start a new project today and it follows this kind of workflow, where you have simulation and experimental data and you want to compare, I would say this is more the way to go. But just for software, copying these two files is more than enough. So far, so good. What about saving data? We already kind of talked about part of this in an earlier lesson. So, for example, using the CSV package, we can dump a data frame into a CSV file. So we just pass it the name of the file and the data frame itself. And this will just write on disk, and we can just, look at it since it's CSV is UMA readable. So that's just how it looks. There are some other, interoperable formats that you can use to share data with people that are not necessarily using Julia. And those we mentioned in our data frames and data formats lesson. So there is infrastructure to save data in JSON format, for example, Parquet. It mostly revolves around, importing the right package. So, for example, for Parquet, we'll use Parquet 2. And we can, just use the write file function. and then we will just, read it back. And that package itself offers infrastructure for that as well. So we can actually do this properly. So we get the data set, we will get the data set itself as parquet2.dataset. This should be all that there is to it, yes. So this data set is an internal data type used by the package, and then we can just, convert it back into a data frame. Yes. And yeah, we're back to square one. We can do the same with JSON. So we can import the packages that we need, JSON tables and JSON3. JSON offers a file type of interface. So this will be used with the open command. And we'll open it in write mode. If you're not familiar with this open do syntax, that's kind of like a context manager in Python, like using with. So basically the result of the open command is brought into this IO object. And then we can call the write method. And JSON tables basically creates a offers a command called object table that changes the data frame into a JSON structure, so a dictionary that can contain lists. Then we finish, and this with a written, and then as usual we can open it or just inspect it manually since it's just a JSON file. Yeah, and then the JSON3 package offers some infrastructure to read the file back. So this will just basically turn the string representation into a dictionary, and then this can be converted into a data frame. This works, or it's very useful to have interoperability with other software ecosystems. Sometimes we're interested in serializing objects to be reused within Julia mainly. And for example, CSV and JSON are good for because of the fact that you can inspect them visually. But that also means that they're not really good at representing floating point numbers, because what we actually save are string representations of the numbers, not the numbers themselves. So there is a trade-off between the precision at which we want to represent and how much space we want to occupy on disk. Parquet, from this point of view, is easier because it's a binary format. But the state of the art when we want to work with scientific data is something binary. And from the Julia perspective, there are two bespoke formats that have been developed during the course of the years. These are the JLD and JLD2 that stand for Julia Language Data. And the JLD.jl was the first one chronologically to have been developed, and provides a way to save and load Julia variables while preserving the types. It's kind of like pickling in a way from Python, but more interoperable, I would say, because it's based on HDF5. that is both a standard and the implementation of that standard, and is probably the de facto way of saving scientific data. So you might have come across it when working with simulation data, for example. Sometimes the weights of neural networks are saved in an H5 format. So the standard is open, and anyone can, write their own H5 implementation. There's also the original, or the standard implementation, that is a C library. And most languages, when you want to interoperate with H5, they just wrap around this implementation. JLD in Julia is written in pure Julia, so you don't have to, bring or somehow ship the original implementation in C with you. And it's a package like any other. So in this case, I think I've already added it, so I can just go using JLD. No, never mind. I can add it now. So this will just take care of, downloading and putting it in my environment right now. The interface of the JLD package is not too different, for example, from the NumPy save and load commands. So I can just give a short walkthrough while this downloads. So we have a save command, and we pass to it the name of the variable in which we want to store the data, and then the data itself. So in this case, I want to save our data frame, and the file itself will look like a dictionary. So the key to this dictionary, in this case, I'm also calling it df. So just to demystify this a bit. df, and then the data frame itself. So now this is saving everything. When we want to load it back, we can use the load command that is still offered by this package. And we could do, for example, just loading it. Let's call this A, for example, load penguins.jld. And when we do this, we will come in a second. Sorry. I have to give it the data frame itself. So when we load this back, sorry, because I overread. Sorry, that's because I had already saved the file with the JLD2 package earlier, and I tried to rewrite that. When we use, sorry, so let me get this from the beginning. So normally we will use this load function, and I promise you that it works. JLD has been kind of superseded in recent years by the JLD2 package. And JLD2 is also based on H5, and I would say it's also more interoperable with other HDF5 implementations, which means that other software that implements the standard can open it, and it can also open the and also other software implements it can open JLD2 files. It exposes an interface that is similar to JLD. So as a save and load functions. But we also have a version of this that is a bit more user-friendly to use, because we can use, for example, this JLD save command. And this, we just pass it the data. And this is exactly the same as the save command that I used above. And then in the same way, I can load it back by just passing it the key to the dictionary. And we also have a JLD open function that provides a file-like interface. So this is, you can look at it, this here, for example. The JLD open function looks a lot like the JSON version. So it gives me an interface that looks like a file, and then I can just write into it. And so nowadays, probably if you were to start from scratch, it would make more sense to use JLD2 that can open JLD, older JLD files, but only in read-only mode. Both of them are used to this day, since JLD is more battle tested because it's been around for a longer time. But yes, I would say that JLD2 nowadays is a bit keeps up more with the newer Julia versions. So that's the one that I will go for. And it also has better support for missing data compared to the older JLD. And yes, I would say this is the end of the tooling part. So if you want to, share software or reproduce software, you can go with these TOML files, or even better, using Dr. Watson. To save data, CSV, or other interoperable data formats. Otherwise, from within Julia itself, you can go with JLD, or even better, JLD2.
Okay, Live 50, welcome back. Let's continue to the next episode about machine learning.
Okay, so today we are going to discuss how we can utilize Julia for machine learning purposes, and what are the key steps in data preprocessing in Julia, how we can, what are there some popular machine learning algorithms that are already available embedded in Julia, how this language can help handle large data sets for machine learning purposes. Even we will also, if we have time, discuss clustering in Julia and classification techniques that are available in this language. And we will have set of exercises. Just 1 second, I scroll here. Like we will have a bit theory and then some exercises, and then continue with theory of this. So machine learning is branch of artificial intelligence algorithms within computer science that focuses on utilizing data and algorithms to imitate the way how humans learn, or how biological organisms learn, gradually improving its accuracy. And machine learning, it's an umbrella term for solving complex problems, which usually, if it's approached otherwise with simpler programs, would be cost prohibitive. So instead, these problems are solved by helping machines, or these mini AI systems, to discover their own algorithms to recognize such use cases and to analyze data. And sometimes there is unsupervised machine learning, which you just put all of your data there and it's somehow analyzed it and can make some predictions, for example. And today we are going to discuss a bit narrow down topic. It's neural networks. So neural networks is a specific choice of the model. It's a network made up of artificial neurons A neuron in this context of neural networks is a mathematical function conceived as a model of biological neurons. So essentially, of course, even classical AI, we can say classical first neural networks, they were inspired of how our brain works. And there are different mathematical representations and possibilities how to represent this model of biological neurons. But there are also some simple description of how this artificial neural net can forms. And I will also show it to you. Just a second. Yeah. Which was taken from Euler Academy Foundations of Machine Learning course, and even some example, just simple brief example how it looks like. So then you can discover this notebook a bit more. So when we would like to build a neural network, we would like to build models and have computer automatically analyze and learn how to match the model to data as its core of how any machine learning method works. And we started to discuss neural networks. It's a network made of neurons, and we can mathematically represent this model of neuron as a sigmoid function. And one of the options that we can use is such formula where we can see x and w are both single numbers, and we can use this function to model how the amount of the color green in image x, for example, can be used to in this example, can be used to determine if image shows an apple or a banana. Because sometimes we can use machine learning algorithms for classification purposes when we need to distinguish, for example, two different objects, and where we have, for example, big data set with a lot of such objects, and we need quickly to separate them into groups. For this purpose, for example, we can use simple machine learning algorithm. And for example, we have this task to identify how many images show an apple or a banana. And it's simple feature, but also there is a possibility to embed to such neural net multiple data features, because it could be not only color, but for example, height, weight of this object we would like to classify. And then we can include in this function we discussed before multiple features in this manner. And now we can see that x and w are vectors for many components rather than a single number. And for example, yeah, x1 can be amount of the color green in image, x2 can be the height of the object in the picture, x3 could be the width, and so forth. And we can add any additional information that is needed for many features as we have. And now, when we did so, our model now has more parameters, and it will help us to train our model. And this version of sigmoid model that takes multiple inputs is an example of neuron. And big like subclass of learning techniques which is based on such concept as neurons, it's artificial neurons, because it's also possible to simulate very similar to biological neurons. It's primitive version of a primitive mathematical representation suitable for machine learning to represent how neurons can function. So this is called artificial neurons. And both artificial and biological neurons have several inputs and single output. So it could look like this. For example, we have four inputs, four neurons, and some connector between them. And this network, simple, very easy network would look like this. Some input, and then the red, it would be some output we would like to discover from this simple neural network. And that's how we can explain this picture. So 4 pieces of input information, it's showed as green on the left, and then the neuron that collects this input information, shown in red on the right, receives all the inputs, processes them, and outputs a single number to the right, some outcomes of this. And in this words, a neuron is just a type of functions that makes multiple inputs and returns a single output. And the simplest case we will check in this short notebook where we have just two pieces of input data. And then we can, for example, draw a network that consists of 2 inputs and produce 1 neuron. And each link between circles above represent a weight, because we can also like if we would like to link, for example, this object, this between this, and how we can how we can link input information to this formation of neuron, and they will have weights that can be modified to allow the neuron to learn. And in this case, the simple model, we have our neuron has 2 weights, weight 1 and weight 2. And then we have also, when we try to build very simple neural network, we need to add some bias. As we human objects, we also have some bias when we're analyzing information. And in terms of neural networks, a bias is an activation function, which will take sigmoid function that we have been using for our neuron and activate it. And for example, let's call our neuron like this, with some input data and with weights. Weights are links between input data and neuron we would like to form, and do like this mathematical formulation. And note that this our neuron has 3 parameters, 2 weights and 1 bias, like weight 1, weight 2, and B bias. And we put these weights into vector to easier analysis. And then eventually we have some dot product where v multiplied to x is when we have both some input data and weights, and in that way we produced very simple neural network. And then you have just short exercise to test it, but I think you can do this on your own later. And also we included in this learning material some references. You can learn more about machine learning, and even one very great simple Google Colab, which you can just run directly from your any device, phone, iPad, or computer, to understand how these simple builds of neural networks and what are artificial neurons are, if you would like to deep dive. So I really recommend this notebook. And now we are going to discuss specifically machine learning, how it's being used in EULA language. And despite being a relatively new language, EULA has already a very strong and rapidly expanding ecosystem of libraries just dedicated for machine learning and even deep learning. And why? Because EULA seems to be really fundamentally advantageous for machine learning, because EULA helps us to solve the two-language problem. There is, first of its aspect, there is no need for different languages for the user-facing framework and the backend heavy lifting, like the most other deep learning frameworks. What I mean by this is it utilizes both simplicity of Python syntax and also performance of computations from, for example, C or Fortran languages. Because we have, if we utilize just, for example, Python for purposes of machine learning, sometimes we can encounter compilation time-consuming issues, for example. But EULA, on the other hand, would execute such models natively more quicker because of fundamental advantage of this language. And particular focus in EULA approach is to machine learning is scientific machine learning. It's also called physics-informed learning. For example, when machine learning, which incorporates such scientific models into the learning process instead of relying only on data. And the core principle of such scientific machine learning is differentiable programming. It's an ability to automatically differentiate any code and thus incorporate it into Flux, predictive models. However, of course, EULA not that developed like PyTorch and TensorFlow, Python implementations, libraries for Python in terms of documentation and API design. But as we discussed many times during this course, that this is a rapidly evolving ecosystem, and EULA is especially suitable on running on supercomputers, and supercomputers are usually for scientific machine learning issues, primarily physics-informed learning, and that's why it's growing so fast, and there are a lot of different libraries. And EULA has a lot of packages for classical, not deep learning, but like we can call it traditional machine learning. For example, scikit is similar like in Python, is a part of the popular Python package. It also includes, if you, for example, it's all of these things are linked. And if you're interested about all of these details, you can check them later. And also, for example, this package provides common interface and meta algorithms for selecting, tuning, evaluating, composing, and comparing over a lot of different machine learning models. There is also, we link a website that lists various EULA packages related to machine learning. There are many of them. And you can check all of these packages by their popularity, alphabetic order, or even updated date. And it's all of these packages have short description, so you can see it's like a lot of different for prediction, for augmented Gaussian processes. Anything you would like, TensorBoard Logger, this famous Google tools for AI, TensorFlow, TensorBoard. So there are even OpenAI API wrapper for EULA. So you can do anything you would like to program with the help of EULA. And nowadays it's super popular. You can see it's like just a lot of different packages already. And you can always easily interrupt any other package from other languages to EULA because it's highly interoperable language. And there are even another website that lists a lot of artificial intelligence packages, for example, BrainFlow, neural net differential equations, transformers, its famous class of machine learning algorithms, and much more. And even an article that discuss some useful EULA libraries for machine learning and deep learning nowadays, for example, for natural languages processing like ChatGPT purposes, things, or computer vision. And today, during our lesson, one of the utility functions, we will use some of the utility functions from machine learning EULA package in our deep learning exercise that we are going to do a bit later, or maybe now. Yeah, maybe now it would be a great time. So what you can do, you can add using package add this one, which we would use. And now I will just a bit jump through this lesson to deep learning, and then we will cover clustering and classification after pause in the next set. So before going to exercise, we will just briefly describe what is deep learning. And it's a subset of machine learning, which in essence is a neural network with 3 or more layers. So that is why deep learning, because it's integrate information within this model somehow through the layers, like deeply. And it could be hundreds or even maybe thousands of layers if you would like to build very complex neural net. And these neural networks, these artificial neural networks, they attempt to simulate the behavior of human brain or maybe other mammals' brain as well.
Да.
Oh, yes, any question? Oh, okay. If you have any questions meanwhile discussing this, please write them in HackMD or Zoom, and my colleagues will parallelly answer if you have something to wonder about. And if someone would like to ask something, maybe now it's also a good short opportunity to do so. Does anyone has any questions?
Yeah, if anyone has questions, just bring this and speak out with in just yeah.
Okay, so if someone they would just speak if they have question, yeah. Okay, I will continue. And these artificial neural networks, they attempt to simulate the behavior of human brain, and they had this ability allowing these neural networks to learn from large amounts of data. And nowadays, deep learning drives many AI algorithms and services that improve automation, performing analytical and physical tasks without even human intervention. And usually, these deep learning architectures, such as, for example, deep neural networks, deep belief networks, it could be even deep reinforcement learning, recurrent neural networks, convolutional neural networks, and transformers like ChatGPT, for example, have been applied to fields, all possible fields, computer vision, speech recognition, natural language processing, and generation. When we ask ChatGPT to do something, then it's process this, and then when it's output some text, it's generating natural language generation. Machine translation, bioinformatics, drug design, medical image analysis is very important field because it really helps radiologists to distinguish for example, cancer images, and it proves to be much, much more better and useful such AI algorithms than professionals within this field. And that is one of the domains where we combine both powers and experience of human beings with these advanced algorithms and really delivering some results out of this science and computer science in general. And its deep learning is also useful to analyzing very big and complex large amounts of data. For example, when we're analyzing climate, we have a lot of features to consider, and you can imagine such an algorithm for simulating or analysis of climate. Climate has a lot of different features like humidity, wind, temperature, and so on. And then we have a lot of these features and we can combine them in artificial neural net, have built a few layers of in this neural net, and in this way it will become deep learning neural network algorithm. And machine learning also even being utilized for different gaming purposes of different kinds. Important package we will discuss during this lesson is Flux. It's already, we can call it batteries included a library, a package that already has a lot of useful tools built in order to execute deep learning algorithms. And this particular package also enables the user to write own Julia code for deep learning components. So this Flux library is very flexible, and it has some explicit APIs for features like embeddings or regularization, which could be helpful when we're designing deep neural network algorithms. And people say that all of Flux is very straightforward, Julia code, and we recommend to inspect this package, and yeah, it could be easily extended if needed. So it's something community-driven, possibility to improve coding. And Flux works well with other Julia libraries like dataframes, which we discussed previously, images, differential equation solvers. And people can build complex data processing pipelines that integrate such Flux models. And today, Now we will have some to do and some short exercises. To install Flux package, you can use, as always we do, using package add Flux. And here we have some to do. I already executed this code and will show you output on my end. And parallelly, you will also have some time to execute it on your own machine if you would like. And our to do is today to train a deep neural network to classify penguins, which we discussed earlier. And to train such a model, we need at least 4 things. Collection of data points that will be provided to this objective function. So we need to indicate some data points, and we will do this with the help of data frames. And we will need some definition of a model, mathematical definition, like our model, for example, will consist of 3 layers, 6 neurons, and it will be such amount of weights between them. So we need to define this. It also needs to access to its trainable parameters, and we need some optimizer that will update our model parameters appropriately. Some optimizer, this kind of bias we intentionally include in our model in order to have some distinguished, in order to distinguish these data points and optimize our solution while we're training this model. And then eventually, how usually neural networks work, you write it, maybe for the first time when you execute this, you get some primitive results, but then you can run this neural network more and more times, more and more epochs in order to receive better results, because a model will train and learn on the way. When we train the model, it's like kind of like a child. It's learn and learn from data points, gathering some insights, and then can have this ability to really distinguish 2 objects. Is it green or is it yellow, for example, because it's learned these properties very well. And within our to-do, you have all of this code. You can just copy paste or copy row by row if you would like. So first, when we start approaching this, we need to import some required models and load the data. And we will use Flux, machine learning package, partition, confusion matrix, data frames, and we will again use penguins data. In the same way, we will load it to the table, we will make a data frame of this, and I have a question to you. If someone can answer in the chat or via voice, what this line of code does. If someone remember from yesterday's lesson. No one remembers this? Okay, so drop missing we can utilize to miss some missing data points, because we have some data and sometimes it could be a bit not enough cleaned. It could consist, for example, data can be shaped into table format, but then some of the rows can be empty because it just things we observed didn't include this data or any other issues that happened. So sometimes data can be like we can say can include some things that we don't need for our model, for our neural net training. And that is why it would be useful to miss some empty points in our table in order not to mess up with our future network we will build today. And so you see, I already executed this code. That's how our data looks like. And then we have in table format and data frame, as you already saw. So we have some table out of our data with rows, species, and then we did this drop missing function. Here on the left, you can see on the left side of my screen. And now we have more cleaned version, preprocessed a bit version of our data in order to work further. But when we start data science applications, data analytics, before building some model, we need to analyze our data, and where it comes data analytics aspects into this. So we have data. It could be not clean. It could include some different things we need to miss, and we can drop missing these things. And then after, before we make it suitable for training a network, we need to pre-process our data set. For example, in this example, we select some features and label columns, and we also split our data into training and testing parts. Like you can see, it's classical way, 80% of data could go to training, and then we can have 20% of data for testing purposes, because when we did some primitive neural networks, we need to then validate how our neural network perform on our data. And that data shouldn't be used into training. So that is why we have some separation. In order to test and validate our future algorithm, we need to leave some data for testing purposes. And that is why we split it like 80% for training parts and 20% for testing of data. And could be done in this way, split into training and testing parts. You can see xtrain, xtest, and partition like this. And on the left of my screen, I already run this. So first step is to select feature and label columns. We did so. And then we split this into training and testing parts, and that's we receive some output of this. And next step would be utilizing single precision and transpose arrays. We will add some just arrays to this data. And then before we are going to build our neural network, we need to encode our data. And this could be done with, in this example, with one-hot encoding. So when we do so, our data is encoded into ones or those other points, just for making this more readable for machines themselves. So, machines analyze information via bits, like whether it's 0 or 1, and that is we encode our data into machine readable format. It could be done with one-hot encoding, but there are other ways as well. And then we will count penguin classes to see if it's balanced. So we will do this step, count penguin classes, and we will get as an output some small integer, some matrix, which consists of this amount, like we have 3 classes of penguins, and first class has 116 penguins, another class 94 penguins, and then we can see it's not super equal number, but we can work with this further. I will describe all of this and show some possible output, and then you will have time to go on your own all of these details. So, okay, we did some counting of how many classes we have, and we checked whether it's balanced or not. And next step would be integrating loss function, which will be minimized during the training. And we will also define another function that will help us that will give us the accuracy of the model. And here we can a bit check it more deeply. So we use cross-entropy loss function. It's a typical function that uses for classification algorithms. Just because in order to let our neural network to train, we need to apply some of such functions like this loss function. And this is what we do in easy way. You see, we define this function. We use flux, cross entropy, like function available through flux, and apply it to our model. It's just one of the examples. There are other types of loss functions that could be utilized. You can learn all of these aspects when you conducting some machine learning projects. And then we need to apply another function which called onecalled, opposite to onehot, that we used here before to have this once to encode our data. And onecalled, it gives back to the original representation. So first we transferred this data into machine readable format. We encoded this a bit, but then we also need a function that will help us to get back the original representation of these data points. And then here in this code chunk, you can see we will utilize for our neural network. We will have some number of features, like, for example, weight, height, or color, for example. We will have some classes. As you know, we saw here that we have 3 classes. And we will apply some amount of neurons. And within this line of code, you can see we have 4 features, 3 classes, and 10 neurons that we are going to use for this current state of our model. Here we did this code, okay. And then we have model. It would be definition of our neural network. How we see it, we can define it in different ways. And we will start with very simple model when we combine in dense our features neuron and sigmoid function for neuron itself, for definition of the neuron itself. And then another layer of this, because it would be first layer, then second layer, and then some optimizer. Softmax is a classical optimization function utilizing for classification algorithms, and there are other types of such optimization functions, because when we build this neural network, we need some kind of functions that would help us to optimize it in order to make some progress, in order to make this neural network to learn somehow within our training processes. And then we will define, I will scroll a bit, we will define an, it's called anonymous callback function to pass into the training function to monitor the progress, select the standard optimizer, like for example, Adam, and extract the parameters of the model. And that is why we will utilize this function for our model. So we will do this like this, callback, considering loss of training data, applying optimizer. It could be Adam, it could be others. There are also many optimizers available through the documentation of different libraries, but this one is the most popular or classical one, we can say. And we apply this to parameters of our model we build. The next step would be before the training the model. We can check some, because now we are in the process of data analysis, data preprocessing, and data modeling within this our test example. And before we jump into training the model, we need to check some initial prediction and accuracy of our current state of algorithm. So here we applied callback function on the left and applied this function. This you can see some output we directly receive from Euler. So okay, here is our optimizer were applied to our data. We added these parameters to our model, and then we need to check some prediction before training the model, and we have such, like for example, output in a matrix of our data points within our neural network, how it predicts what class it would be in that particular data point in our tables that we formed from penguin data. And then we can check its accuracy. You can see it's very low at the moment, so accuracy before training is less than 50%. And while conducting the training of our neural network, we aim to increase accuracy because, for example, as it's higher, then we can be more sure in the results. For example, when we need to distinguish two different objects, whether it's green or red, we need to be sure with high probability, 99%, that this is really green thing, that is really what we want and need. And especially it's useful for computer vision, for example, to analyzing amount of cars on the road, how dense it is, and we need to be sure to receive good results. So for example, for many applications, 40% of accuracy would be very low. Usually we aim to much higher accuracy, but it depends on purposes of your algorithm. Sometimes you don't need maybe the highest accuracy possible. And that is why accuracy shows us really how our neural network performs. So it's very key indicator of what we are doing. And we checked, you see, accuracy of our training data and our test data. So it's random results, but it has low accuracy anyway. And then finally, on this step, we are ready to train our model, and we will do this 100 times. It's called epochs in AI machine learning, like one epoch, one time. So we can train it 100 times. And here you can see in this data chunks that the training data and the labels can be passed as tuples to train. Tuples are immutable sets of data points. And we do this 4 point in this place, train, apply flux features packages to this. So you see this package that we initially downloaded. Flux, train, we have some loss function embedded. We have our training data. We have some optimizer like Adam. And in this way, we got some simple representation of how we can train our model. And then after we do this training, we can check final accuracy to see whether our algorithms had been improved or not. And then you can see on the left of my screen, I started before the lesson, I trained the data, and it was, in this example, we have a very primitive example, and this function can be executed super quickly. So if you run it, you will get this output just after a few seconds. But when we are handling in real case scenarios, when we are handling very big data sets and training data, this process can take time, can take a few days, weeks, months, or more. Some GPT models, these language models, like OpenAI, they were trained maybe a few months to get good accuracy, or maybe even more, because it takes a lot of time, even with high-performance supercomputers. It still takes time. But nowadays, we people, engineers, programming community, we are trying to improve accuracy of both programming languages, of software, of models we are building, of software part of this to make it more efficiently executed, like emergence of this Julia language, it's efficiently executed, but also to build dedicated type of hardware, specifically, for example, for concrete purposes. Nowadays, we see in EuroHPC projects, it's being procured to build dedicated for AI, for machine learning purposes, hardware machines, because they also need to be built physically in a specific way to analyze all of these matrices, all of these data points, somehow very efficiently. Like, for example, our brain analyze information. It's kind of efficiently to some degree. And okay, we trained our data we did 10 epochs, so you can see the output. So we applied loss function to this, okay, and then we checked final accuracy, and the results are, we can see final accuracy after our current state of training hadn't been improved that much. It's still very low accuracy. And that is where we are jump into exercise section, when you have time to improve this deep learning model, and you will have some guidance, and always the solution is available, where you can do the same steps I did before, build your very simple deep learning model, and then try to improve its performance. And there are different ways how you can do this. You can improve performance to activate another type of function, or do batch normalizations, or simplify data, or have more epochs of training, because maybe from 10 times you will get pure results, pure accuracy. But if you train this neural network hundreds of times, like maybe 200, then you might get a better result. And we will see and discuss it after you conduct these exercises. And then we can discuss your outcomes of this, what helped, what accuracy you received, because it intended these exercises that you will get better final accuracy. So it could be up to 80% or 70%. It depends on how you will approach this. And there are even, then after you do these exercises, we will discuss some even more improvements we can do, and additional exercises. But now let's dedicate some time for these exercises, and then we will have pause, and then we will continue with our lesson. Okay, then I will share the screen to continue about clustering and classification. And we will also, so we explored a bit what is machine learning in general and what is deep learning. And there are also other types of machine learning. There are many of those types, but the most popular ones are clustering and classification. And within this lesson, we will explore ULE for high performance data analytics in Jupyter Notebook environment within Visual Studio Code. And I will show you this notebook. It's on the left on my screen with all of the outputs. I pre-run this before and got the outputs, and we will check. And then on your own after this course, you can download and set up this environment if you would like to test, because I think it may take time. Or in preparations, people already installed ULE into Jupyter Lab and Visual Studio Code. How is it? Would it be possible to run some exercises? Or is it maybe too complicated and people can do this later? How you suggest, Young?
We can continue the lecture session and then leave the exercise later.
Okay. Yes. But we have described in ULE intro lesson on what was on the first day, how to set up environment and how to get ULE executor within your Visual Studio Code, and when we can use Jupyter notebooks. But I will show you how it looks like from my computer, and you might have similar setup later on. And once we have our environment set up, we can start using ULE in Jupyter notebooks within Visual Studio Code. And this, from my perspective, this setup provides powerful interface for writing, debugging the code, and easily visualize data and results from one window, and not necessarily you don't need to open any other executor or something. And we had adapted some lessons about clustering and classification from ULE MOOC, which is massive open online courses on ULE Academy. And for more different details and tutorials, you can go there and take this, because it's free and open, and all of the materials and exercises available there. But today we focus on clustering classification tutorials for deeper understanding how to use ULE for high performance data analytics. And maybe I will restart sharing the screen just to share the left side. So 1 second. Okay, what can you see right now, Young Lei?
Just the waste code.
Okay, good. And you can see well, no need to increase, so it's...
Probably can a little bit wider of this.
If I do like so, will you see
Okay.
this?
Yeah, much better.
Okay, oh, great. Thank you very much. So clustering is a type of okay. When we discussed machine learning, we touched a bit that machine learning methods could be supervised by human, where we control the environment, or unsupervised, when we just put a lot of data in our model and it somehow analyzes it and we don't have control or overview of everything what happens. And sometimes it's called black box AI, where we are not sure what exactly being done, all of these things, how this learning is being done through this network, but we can control it a bit. And one of the types of such unsupervised machine learning methods is clustering. Is a method where the model tries to group the input data into clusters based on their similarities of data points into within this model and data we utilize for this. And clustering is commonly used for specific problems into two-dimensional data, where the goal is to create clusters based on coordinates. And today we will use something similar. We will cluster houses based on their latitude, longitude locations using several different clustering methods. And this notebook are available through lessons materials. You can just directly download them and try after these lessons if you would like to have some more insights. So what we are do as a first step, we need to import all necessary packages, as we always do in ULE. We can do it import package and package add, and we will use clustering, some database, JSON, data frames, and comma separated files, SSV. So we will utilize these packages, and then we add them to our environment, and then click like write using these packages in order to utilize them through our notebook and make ULE execute them. And I did these steps already before, and we can see them output. And when you do so, you will get the similar outputs. We will start by getting some data. And this is a good example of how you, for example, you're a data scientist, you're in your Visual Studio Code in Jupyter Notebook environment, and you can download from internet in this very easy manner some data, from example, from GitHub, some data set with new houses and housing information available there, and you just download from this resource and then read it as a SSV format into data frame. And that's the output we will receive. We will receive the table with all the information needed, how many rows, what the longitude, latitude, housing, their total rooms available, and some information from our data. In visual, human readable way. And this would be your first step in data analytics, because you need to download data and first check that in available for you format, in data frame format, for example, what you have, what insights you can grasp from this data, what can you analyze possibly from this, and already start simple pre-processing or featuring engineering aspects. And then what we need to have, we need to see all the possible, for example, names within our data available. And then we can run simple code line and receive some topics, some columns that we have within our data. And we see we have we can consider we have some vector with information like longitude, latitude, total rooms, population, household, median income, ocean proximity. And this is some of the features we might take into account when creating our clustering model in order to analyze this data and get some insights from these processes. And in this notebook, we will use a Vega Lite package for plotting in order to create nice plots. And this package makes it very easy because when we doing data analytics, we need a lot of to visualize data to see what is there inside, to see it in a human readable way. And usually it's good to plot on a way, and that is why we will utilize this package. And this package makes it very easy to plot information on a map. And what we need only is JSON file of the map we intended to draw. And here we are going to use California counties, like the map with all buildings in California, and it would be JSON file format. And then we will plot each house on the map and color code it via heat map of the price. And we will get some insights over this. And this is how we can use some color our map. And here I have exercise. You can do them later after this tutorial if you will have time. And the solutions available at the end of this notebook. If you will stuck, for example, you just can scroll down to the end of this notebook and you will get solution for these exercises. But here would be the line that we have this data, we need to load this for our purposes. We have to load this JSON file, you see it, JSON file, and it will be in the same way as we did here. Just download from this data and then have it in a readable format. And I already conducted this, and then we will use this JSON to visualize it. And as I mentioned, we will use this Vega plot. And then there are some, some information about colors you would like to add, how you would like to represent values, so some just data visualization. And that's what be the output we receive from this code. You see it's hot hit colored, and we can see like median house value, for example, near sea, it's higher prices for these houses. This is what insights we can gather from this very first steps of data analysis. Even before we jumped into actual training of the model or something like that, we already can gain some insights by visualizing the data. Then we again check what columns we have. And also, okay, then will be its next stage, which we'll try and explore in this notebook, is if clustering the house has any direct relationship with their prices. So, for example, we will bucket the houses intervals of specific sum, and then perform the color codes based on each bucket. And this, again, we will utilize this package and do some visualization. And this can take some time, a few minutes to run. So don't be scared that it's just being processed, because it's a lot of complex visualization of data, and it can take a few minutes to process this. And that would be the result we receive out of this. And it also can provide for us some insights. After we did some some first data analysis, we can go to the clustering topic in itself. And there are could be types of clustering. And here we will explore key means clustering is a specific method within clustering domains of such algorithms of vector quantization, originally from signal processing, and it has the aim to partition observations into clusters. So we have some n observations, and we would like to make them in key type of clusters. And each observation would belong to the cluster with the nearest mean. It's also called key nearest means. And what we mean by that, By mean, we mean cluster centers or cluster centroid. And we will form the clusters of our data and separate it based on some of the observations. And this result in partitioning of and we will get results partitioning of the data space into Voronoi cells. And then you can read more about what it means. And this k-means clustering algorithms works as follows. Firstly, we start processing by randomly assigning each data point to initial group and then calculating this centroid for each one. A centroid would be the center of each group. And in this way, we shape the first clusters. And then we will evaluate each observation, assigning it to the closest cluster. So this our model we will write. It will make some observations, evaluate them from the data, and then assign those data points to those different clusters we pre-made in the step one. And definition of closest is that the specific mathematical Euclidean distance between a data point and a group centroid. It's shorter than the distance to the other centroids, and in that way it can clusterize this information. Within this, our model we're trying to build. And then we repeat this algorithm until we no longer can assign data points to a closer set. So we do this as long as it's needed. And when this clustering algorithm finishes, all groups have the minimum within cluster variance, which keeps them as small as possible. And sets with minimum variance and size have data points that are similar as possible. And in this way, we will have the necessary clusters of this data and its features. And this type of machine learning is popular because it's unsupervised method, meaning it starts without labels and then forms and labels group itself. And it's often suitable for situation where you don't have existing group labels. However, you would like to make these clusters and to assign similar data points to the number of groups you specify. And firstly, what we need to do when we do these processes is defining data as a matrix. Just it would be more suitable for clusterization of this. In order to do this k-means eventually, we need to use this matrix, and we will do 10 clusters out of this. And that's the output we received, some, again, data frames clusterized. And then it will be another exercise when we can visualize this, and you have also the solution at the end of the notebook, how we can do that type of clustering. There are also another one, k-medioid clustering is similar to k-means, but instead of using the mean point as the center of cluster, k-medioids use an actual point in the cluster to represent it. And it's this kind of method is even more robust to some noises and outliers in our data we use. So sometimes for some purposes, this method could be even more precise. And we have some description here. You can check it later, I think. But just a aspect of this type of clustering, we need to build for this a distance matrix, and then we will use specific distance packages for this purpose and compute the pairwise Euclidean distances in order to analyze this. And there are some reference to these methods if you would like to explore it more. So we do this type of matrix and then assign k-medioids. Also, we can have 10 clusters of such, and we will get this type of clustering over our data. Then we can plot this, what we did, just to check some insights. And you can see within these plots, when we did k-medioids clusters, now we did this method, we don't see very big separation, or it's not super helpful for our data we are currently analyzing. So maybe we will not proceed further with this particular type of clustering because it's not super suitable. But when you do data analysis, you also need to find the best method for your data. So you might check different types of methods, and you will gather some first insights whether it's even useful to proceed further with such methods just for this specific data you're using, or the task you would like to, the challenges you would like to identify within this workflow, machine learning workflow you have. There are also other types of clustering, like hierarchical clustering, which trying to build a hierarchy of this cluster from less important to more important. And in Euler, we have even a separate, a special clustering package, which provides different features, and you can test it and explore it. Includes different clustering methods. And for example, in case of hierarchical clustering, we can use a specific function to perform this. And in essence, such clustering algorithms, they build a dendrogram of nested clusters by repeatedly merging or splitting clusters. And for some purposes, it could be useful. And here we did do again a step with trying to clusterize our data in this manner. And then we will do some visualization again, and we will see some data output of this. Like we have this hierarchical different clusters. You can see that the orange is like less represented, and we have the most like when gray is less represented, number 10, and for example, blue is the most amount of data points we have because it belongs in accordance with this approach to this specific cluster. And it might help us with our analysis of the data, and we might gain some insights out of this information. Then there is also another type of clustering, which called density-based spatial clustering with embedded noise. And its type of clustering, it's like using non-parametric algorithm. For example, given a set of points in some space, it groups together points that are closely packed together. Points with many nearby neighbors, marking as outliers points that lie along in low-density regions, whose nearest neighbors are too far away. And this one is the most common cited clustering algorithm, so might be interesting to explore. And you see we utilize distances packages for this, analyze our matrix of data, have some Euclidean function here, and then we will see like how many unique assignments we have after cluster in this way. And we can see out of this code that we have 15 different lengths of this density-based spatial clustering. Then we again check our data and visualize it in a similar way we did before. And we can see with this method that some clusters, like orange one, are more represented within this data, and also gain some insights after of this. And when you run this notebook, you will gain some insights about key means, key medioids, hierarchical clustering, different types of clustering, how you can modify your data frame, and how you can create nice looking plots in order to describe to other people what insights you as engineer gained from this data set. And just one general cool finding out of this notebook, that when we did these different types of clustering analysis, prices in California do not seem to have an exact mapping with geographical locations. In specific, performing a clustering algorithm on the houses dataset, we didn't reveal a mapping with the price ranges. And this indicates that prices relationships to geographical location is not necessarily based on neighborhood, but probably other factors like closeness to the water or closeness to downtown. But within this example, we proceeded with some data analysis, and we find out whether clustering algorithms actually might help us to gain some insight from this or not. And another notebook we have available is about classification. It's maybe a bit easier approach than clustering to just understand what is this. And it's also adapted from Euler Academy. So classification is a supervised, before clustering, it was unsupervised type of machine learning, but classification is a supervised machine learning that involves predicting the class of a given data points, and it's in a very controllable manner. And these classes can be targets, labels, or categories, or features. If we tell it very simply, classification is the task of predicting a label for a given observation. For example, you are given certain physical description of an animal, and your task is to classify them as either a dog or cat. And for that type of problem, you need classification algorithms to help you to classify different types of objects. In our tutorial, we will classify iris flowers, and we will see that when we use different classifiers, we will compare them also, and we will find out what was the most accurate function. And we will use through this notebook a simple accuracy function that returns the ratio of number of correctly classified observation in regards to the total number of predictions. And common classification algorithms includes kin nearest neighbor, decision tree, naive bias, and artificial neural networks. I will try this. I'm not sure it will be executable. Okay. Okay. So we, as always, need to import some packages, and you will see we use R database, machine learning base, plots, decision tree, distances, nearest neighbors, linear algebra for these purposes, some data structures. This package is what we need. We use them, and then we need first to gain some data. And iris dataset is very popular classical dataset within machine learning, and it's usually embedded in many packages because it's so popular and classical for easy examples of how to train neural networks. And so you see, we don't need to download it from GitHub, for example, as we did with clustering data, but we just do this function and we will get this dataset because it's usually embedded in simple machine learning dedicated libraries packages in both Python and Julia, so it's already there. So with this simple line, we'll get iris dataset, and we have it as a data frame. We can see that we have rows with sepal lengths, widths, petal lengths, and widths, and also categories of different species. And if we do matrix out of this, we can see categories. We have two types of categories, Setosa or Virginica. And this how, if we just write this X, we will see matrix output, how many data points is in this table are dedicated to specific category or feature in the columns we checked here before. Like we have sepal length is this number, petal width this number, and then we can represent it in more machine readable format like this matrix. And X is a matrix that contains features of the iris dataset. And this dataset consists of measurement of 150 iris flowers from 3 different species. And we measure 4 features of this data. Sepal length, yeah, these features we discussed. And by doing, for example, this code of line, we can extract these 4 features from the data set and storing them in X. And the reasoning to doing so is to understand the structure and properties of our data before applying machine learning algorithms. And this could include different steps. For example, we can check the size of our data, looking at the range of values of each feature, visualize the data, because understanding your data can help you choose the best and the most appropriate machine learning methods in order to interpret the results correctly. Because you might have great data, but if you don't know what method to apply, you might not gain insights from this data. So that is why you need in the data preprocessing, data engineering, analytics stage to have different options to try them and see what promisingly shows the best results before even you start to apply some neural networks. And we use such labeling and mapping to transform the labels into integers. And this label code function takes the mapping created by the label map and the original labels and returns a vector where each original label is replaced by corresponding integer. And this is often classically done in machine learning when you have categorical labels like this species or another species. And many machine learning algorithms require numerical input and output, so it's common to encode categorical labels as integers. And we will do this step. So you see we have 3 different species, and that is we have for this data point is number 1 vector because it's part of this species, and this we encoded even more to have to help machines to analyze this data even more efficiently. And in classification, we often want to use some of the data to fit a model and the rest of the data to validate. So that is why we will do training and testing data separation. And we do this in this way. And then we have a specific function inbuilt in EULA that returns a random subsequences of a given sequence. It's called round subsec, and it's used in our here in our this function per class splits to select a random subset of indices for each class in order to have separating for training and testing data randomly, but also a bit controllable way that it would be not super purely random and it could be useful for our future analysis. So we have, in this example, we separated 70% to the training data and the 30% to test data, and we get some vector output of this. And in order to continue with this classification algorithms, we need one more function that will assign classes based on predicted values when these predicted values are continuous, like 1, 2, 3. And this is necessary because when such predicted values are continuous, but labels are discrete. So this function works by finding the class label that is closest to the predicted value. Simple function, just useful for our algorithm. Yeah, I think I will just continue with this and people can then do exercises later on because I think even to set up environment might take time and we don't have so. So one of the methods we can use is lasso method. It's a type of regression analysis method that performs selection and regularization in order to enhance the prediction accuracy and interpretability of statistical model it produces. And in EULA, we can use specific function from this specific package to fit a generalized linear model via penalized maximum likelihood, which is the principle behind the lasso model. And you can read more details about this within EULA documentation and why it might be useful. So when we do such method, we perform cross-validation to find the optimal penalty strength and cross-validation is a resampling procedure using to evaluate machine learning models on limited data sample. And this procedure has a single parameter called key that refers to the number of groups that a given data sample is to be split into. So this is just specific methods and steps we can do in order to have the optimal separation into training and testing data, and even to find out the optimal penalty strengths for our neural network. And from this code, we can see that we have 72 different models and for 4 predictions. And the best would be to use such value with the mean loss, this one and this. So we can utilize some already pre-built solutions in order to see what type of feature, like what loss we might indicate, what things we might indicate within our neural network when we encode it in order to have the best performance, even before we jump into further steps. And this output will indicate that cross-validation was performed with 72 models And the best it would be to use such mean loss and standard deviation of this amount. And this way we are preparing our data correctly for machine learning algorithms we will use later on. And yes, we do the steps to find out the best separation on training and testing data. And when we do this method, then we can check the accuracy of these predictions, and it's 1. So the results suggest that the model is effectively capturing patterns in the data and could be used to make reliable predictions on the new data when we use this method in classification domain of algorithms for machine learning. There is also another method, rich regression, which help us improving the conditioning of the problem and reducing the variance of possible estimates. And then we have a dedicated penalty, which is introduced as a sum of squared residuals in our original least squares regression. It's complex words. You can check these details within this notebook later. And usually rich regression is often used when the number of predictor variables is a set exceeds the number of observation, or when a data had multicollinearity, like there are a lot of possible correlations between predictor variables. And such rich regression is very useful for chemistry, econometrics, like for complex data sets that might concede different correlations between items inside, like for some chemical problems when you have a lot of different properties, and who knows what would be the most helpful for you to get some insights from this analysis. And you have some details there. Another method is ElasticNet, is regression methods that combines some penalties of the lasso and rich methods, and it's kind of combination of those two methods. And it's also could be used from scikit-learn, and like we use both of the previously discussed methods, lasso and rich regression. And it's this ElasticNet method, use each of them when it's appropriate in a special case. And then we will use this function and feed the model to the training data. So sometimes we can feed the data to the model, or we can do vice versa, feed the model to the training data. We perform cross-validation to find the optimal penalty strengths, make predictions on the testing data, and then calculate the accuracy of predictions. And when we do all of these steps, we also get very good accuracy, like 1. Yes, it classified the iris dataset very well. Another method is decision trees. It's also supervised learning method, non-parametric, when it's used for both classification and regression tasks. And the goal of this decision tree approach is to create a model that predicts the value of target variable by learning simple decision rules inferred from the data features. And here we also have some detailed explanation step by step how we do this, how the learning being done. So the process of learning a decision tree from data involves determining the best feature to split on each node, and also often done using measures such as information gain or gene impurity. We can do some predictions out of this, and this method has decision tree. For some tasks, it could be very advantageous, for some not. So it depends on your model, but promising advantages are decision tree are popular because they're easy to understand and interpret. So it's easy for beginners to test such algorithms, and can handle both numerical and categorical data, which is useful for big data sets or when we don't know the best features or categories for that data set. And it can handle multi-output problems. But it has also some disadvantages because it can create over-complex trees that overfit the data, and it could be unstable because small variation in data might result in completely different trees being generated. So it depends, but it's very classical supervised machine learning method. In our case, we will use also the package decision tree that exists through Julia, and we did some very simple, not very depth decision tree classifier, and we run this, and we also get great results because it's simple data set and it's easy to classify what iris species is that. Another method is random forests, is also very powerful machine learning technique that both use regression and classification problems, and it's ensemble learning method, which means it combines the predictions of multiple machine learning algorithms to make more accurate predictions. And we can use, for example, decision trees, feature randomness, and all of them analyze. And for example, what we can gain from this for a classification problem, the output of random forest is the class selected by most trees, majority vote. For regression problems, it's typically the average prediction of all trees. Advantages of this, it can correct decision trees habit of overfitting to training data set. So we can use firstly decision tree and then apply random forest, and in this way we might get a good setup. And because decision trees generally and random forests are usually outperform decision trees and are robust to outliers and nonlinear data. And they also can handle large data set with high dimensionality, like chemical data set. But disadvantages, they are not so easily interoperable, not so easy for human to grasp what actually computer made. And it also can be computationally intensive depending on the trees and its depth. But supercomputing is useful here for such complex data analysis. There are more exercises to explore this method. There is also nearest neighbor method. You can learn more about this. Support vector machines is very popular supervised machine learning method that use classification for two-group classification problems. And it's one of the disadvantages of this, if the number of features is much greater than the number of samples, then we can have some overfitting. And it might be time consuming and computationally expensive. So sometimes it's not a suitable method. But we also explore through this notebook how it works. And it also has good accuracy. And then, just as a last step of this lesson, if we check all of the different predictions we made and analyze them, support vector machine, key nearest, random forest, lasso method, we will see it had all of this had great accuracy. And the funding of this, final funding of this notebook, we used multiple methods to run classification on a real data set. And here is the scoreboard, what method showed which results. For example, decision trees has a bit lower accuracy score in this setup. So we check different machine learning approaches, and you can have more details. For example, there is very good 60-minute tutorial how you can use deep learning with Flux. The future is then also a good suggestion is the future of machine learning and why it looks a lot like Euler, why Euler is specifically good for machine learning purposes, and even some deep convolutional generative adversarial network that you can check, very good tutorials. And as a just final comment, today we discussed Euler machine learning, it's classical domain, but for within artificial intelligence topic, there are also two other emerging fields, very important, and Euler also very helpful with this, is neuromorphic. It's really super similar how natural biological nerve system works even in a more way, because we discussed today that even the very first AI, artificial neural networks, they're also trying to simulate how the brain works, but in a primitive ways. But neuromorphic is more similar, more intrinsic. Is this domain of computing, of probabilistic learning, is really trying to analyze nature, how it really works because of its stochastic programming way. And there are dedicated packages within Euler dedicated for neuromorphic, for spiking neural networks and this domain. And you can, we have also Nordic neuromorphic community, when you can ask our Swedish researcher, neuromorphic researchers about this topic, what they use, and to know more about this, you can join this community. And also, it could be quantum version of artificial intelligence that could be also very useful for some of the very complex problems. So there is a domain of quantum machine learning. There are a lot of Julia packages for quantum mechanics, for quantum AI, quantum machine learning. And if you would like to know more, we have also Swedish Quantum Society set out by NCS, with also Discord, LinkedIn, when you can gain insights and be alerted about quantum events we're conducting through such community.